This call is now being recorded.
So good morning to all. I welcome you to the second lecture for the heat transfer. All of you are able to hear me? Okay. Okay, fine. So I will start with the lecture now. So in the last class, we have discussed the introduction and the handout. So today I am going to start with the chapter number 1, that is the basics of the heat transfer. So before I start this chapter here, I would like to show you about the textbook. Please switch off the webcam and microphone when you join. So, so in your Google Classroom, you can see I have uploaded the textbook here, textbook.pdf here. In your this introduction and course handout, under this title introduction course handout, I have uploaded the textbook. Same I have uploaded in the uh, Moodle also, the textbook under the course handout title. So you can refer the textbook there, and I will be also referring the textbook and mention a few points there or discuss some examples from the textbook. Now let us move to today's chapter, that is chapter number 1, that is basics of heat transfer. So in the last class I already discussed the introduction about it. So we discussed about what is heat transfer. So heat transfer is energy in transit due to temperature difference or the transmission of energy from one region to another as a result of temperature gradients. Also, we discussed that the thermodynamics gives us idea about the amount of energy interactions when a system is interacting with surroundings or with another system. So the thermodynamics gives us the idea about the amount of energy transfer, but it does not give us idea about how much time will be taken for a process to be carried out. So determination of rate of energy transfer, that is the heat transfer, the times of heating and cooling is the subject of the heat transfer. So thermodynamics tells us how much heat is transferred and final state of the system, while heat transfer tells us how heat is being transferred, with what modes, and at what rate heat is being transferred, or what is the time taken for the heat transfer to take place, and what is the temperature distribution inside the body. Also, we discuss about the various applications of heat transfer in day-to-day life. So in almost all engineering applications, heat transfer is involved, ranging from power plants to household appliances such as refrigeration, air conditioning, car radiators, electric iron, and many more. Now today we will start with this chapter 1, that is the basic concepts of heat transfer. So I will start the chapter now. So I will stop presenting here. You can open the slides. I have uploaded the slides in the Google Classroom as well as on the Moodle. So you can open your slides in the background. Okay. So as engineers, it is important that we understand the physical mechanisms which underlie the heat transfer modes, and that we be able to use the rate equations that quantify the amount of energy being transferred per unit time. So the heat can be transferred using 3 different modes. The first one is a conduction, that refers to heat transfer that will occur across a medium. Second mode is a convection process, that refers to heat transfer between a surface and a moving fluid. So you can see here in this PPT, first figure I have shown for the conduction here, where the heat transfer is taking place from a higher temperature T1 to lower temperature T2 through a medium. So this is, let us consider this is a plain wall or some material. So through the medium, this process takes place. While in convection, there is a surface of any body, and over which there is a bulk fluid motion, which is convecting away the heat from the surface. So convection refers to heat transfer between a surface and a moving fluid. So if there is an absence of bulk fluid motion, in that case the heat transfer mode will be considered only by conduction. Now the third mode of heat transfer is radiation. So all surfaces of finite temperature emit energy in electromagnetic waves. Hence, in absence of any intervening medium, there is heat transfer by radiation between two surfaces at different temperatures. So if there are two surfaces at different temperature, and if even if there is no intervening medium, since this conduction and convection was requiring a medium to happen, while the radiation process does not require any medium. So when in absence of any medium there is a heat transfer between two surfaces, then that mode of heat transfer is termed to be as the radiation. Now we will discuss each of these modes in detail, the basic laws which governs these modes of heat transfer. So moving to the slides here. Are you able to see this presentation? Okay. So the first mode of heat transfer is conduction. The first mode of heat transfer is conduction. So we need to define what is conduction first. So conduction is the transfer of heat from one part of a substance to another part of the same substance, or from one substance to another substance in physical contact with it by microscopic collision of particles and movement of electrons within a body. So if you see the slides here, so yeah, so you can see the slide here. That is slide number 8. So you can see, let us consider that there is a rod, okay, a simple iron rod, and if you are heating from one side here, you are subjected to heating from one side, the molecules here are going to gain energy. Molecules or atoms of the material are going to gain energy at this particular end and tend to supply the energy to the adjacent molecules or the atoms. And similarly, this rod gets heated along the length. And if you are touching the rod at the other end, after some amount of time, you will feel the heat or feel the amount of the temperature increment on the other side of the rod. So this indicates that there is a heat which was being transferred from one of the end to the other within the medium without any bulk motion or without any other mode involved here. So this process or this mechanism of heat transfer, where there is a transfer of energy from the more energetic particles of substance to the adjacent less energetic ones as a result of interaction between the particles, is termed to be as the conduction. So that is the definition of the conduction. Now in solids, the heat is conducted by two mechanisms. First one is lattice vibration and second one is by transport of free electrons. So in solids it occurs due to lattice vibration or by transport of free electrons. Okay. So the faster moving molecules or atoms in the hottest part of a body transfer heat by impacts, some of their energy to the adjacent molecules in case of lattice vibration. So when there is a solid and it has a closed packing structure, okay. So when the one side or one part of the solid gets heated up and it gains energy, it transfers the heat to the adjacent molecules by coming in contact with them. The high energy molecules start vibrating and they transfer the energy to the adjacent molecules. So here in solids, the one of the mode by which the heat is being conducted is by lattice vibration. Now the second one is by transport of free electrons. So metals are good conductors of heat and conduct heat better than other solids do. So in metals, some of the electrons are not stuck to the individual atoms but flow freely among the atoms. The free electrons in the newly hot region have more momentum than those in nearby cooler regions, so they tend to disperse in the case of metals. Now, if we talk about the gases and liquids here, so in gases, the kinetic energy of a molecule is a function of temperature, and these molecules are in a continuous random motion, exchanging energy and momentum. So here molecule loses energy by collision. So here two important parameters comes into play, that is the diffusion of heat, that is from a higher temperature side to the lower temperature side. Along with that there is collisions. So I can say for gases both collisions and diffusion comes into play. Now if we talk about the liquids, in case of liquids the intermolecular forces comes into play. So when there is an increase in temperature, the intermolecular forces are going to decrease and the molecule tends to move and collide with each other, and hence they exchange the energy from a high energy molecule to the low energy molecule. So in case of liquids, liquid and gases, case of liquids and gases, the mechanism is by diffusion and collision. So if you have any problem to this point, you can ask. So let's move to the next part. So let us consider that there is a plane wall. Let us consider that there is a plane wall here. Okay. And let us consider one of the side is isothermally at a temperature T1. On the right hand side, this side is isothermally at temperature T2. And let us consider the thickness of this plane wall is delta X. Okay. And the area of this plane wall through which this process of heat transfer is taking place is A. Okay. So the heat transfer is going to take place from high temperature to low temperature. So let us consider T1 is greater than T2. Okay. So this would be the direction for your heat transfer. Now, if you define here A, remember this area A is area normal to the direction of heat transfer. Area normal to the direction of heat transfer. This is very important. So whenever you are making any analysis for a heat transfer, always you have to consider while conduction, for conduction, area normal to the direction of the heat transfer. Okay. So if you see the rate of heat conduction through this medium depends upon few parameters, that is first the geometry of the medium, second would be its thickness, then material of the medium, and the temperature difference across the medium. Now, if you see here, the amount of heat transfer during the process is denoted by Q. The amount of heat transfer during the process is denoted by Q. Now, the amount of heat transfer per unit time is called the heat transfer rate. So, it is denoted by the rate of heat transfer. Heat transfer is denoted as Q dot. That is the rate of heat transfer. And its unit is joule per second. Its unit is joule per second. So that is watt. The unit of the rate of heat transfer is watt. Now, if the rate of heat transfer is available to you, the total amount of heat transfer during a time interval, say delta t, can be determined as Q equal to 0 to delta t, from time 0 to some time delta t, Q dot into dt. So if the rate of heat transfer is known to us for a particular time period, I can determine what is the value of the net value for the heat transferred in a system. Now, the rate of heat transfer, this rate of heat transfer per unit area normal to the direction of heat transfer is termed to be as heat flux. So, heat flux is defined as equal to Q dot upon area normal to the direction of heat transfer. So, the unit for the heat flux would be watt per meter square. So that would be the unit for the heat flux. So for heat conduction, the rate equation which is used to compute the amount of energy being transferred per unit time is termed to be as the Fourier's law. So what I was saying, that for the heat conduction, the rate equation which we are going to use to determine the amount of energy being transferred per unit time is known as the Fourier's law. So the basic law of heat conduction is known as Fourier's law of heat conduction. So the Fourier law of heat conduction states that the amount or the rate of heat transfer per unit area is directly proportional to the temperature gradient, that is Q dot upon A. That is the rate of heat transfer per unit area normal to the direction of heat transfer is directly proportional to the temperature gradient, that is dT upon dx. Or from here I can write Q dot is directly proportional to area into dT by dx. Now the proportionality constant here is given as Q dot is equal to minus K A dT by dx. So this is the Fourier's law of heat. This is the Fourier's law of heat conduction. Now where Q dot is the rate of heat transfer, dT by dx is the temperature gradient across the medium, A is the area normal to the direction of heat transfer, while K here is known as the thermal conductivity of the material or the medium. So if I see this example of plane wall here, that is where the heat transfer was taking place from high temperature T1 to low temperature T2 across a medium of thickness delta X. So I can write from Fourier's law of heat conduction here that is q dot is equal to minus ka into T2 minus T1 upon delta x dt by dx. So here you can see the temperature is varying from T1 to T2, and if you consider this to be positive x direction here, so its temperature is decreasing from x equal to 0 to x equal to delta x from T1 to T2. T1 to say T2. So you can see your temperature gradient is negative here. This dt by dx is negative here. Since temperature is decreasing in positive x direction, so your temperature gradient is negative here. So you can see here, when I have written from this part, that is q dot is directly proportional to a into dt by dx. So from here q equal to minus ka dt by dx. So why negative sign here? Because this dt by dx is negative, is having a negative sign, while this rate of heat transfer here is having a positive sign. So we need to have a negative sign here such that this negative sign get cancelled out and rate of heat transfer will be a positive quantity. So from here, for a plane wall, I can write from here q dot is equal to ka, can take negative sign inside, it would be T1 minus T2 upon delta x. Or this can be also written as T1 minus T2 upon delta x upon Ka. Or this can be also written as Q equal to delta T, that is temperature difference across the medium, upon delta x upon K. This is the Fourier's law of heat conduction. Clear up to this point? You can respond in the chat box. Now we need to define Okay, so I have switched on one more microphone. If there is any problem, you tell me. Okay. So what I have discussed till now, did you listen to it or not? Okay. Okay, fine. So I will move forward now. Hope you are able to see the paper here. Oh, okay. So you are not able to see the paper. Okay. Just give me a minute. Now it is visible. I hope now it is visible. Yeah, okay. Okay. So yeah, now you are able to hear me and see the paper. So what I was saying that echo is there. Now it is okay. Okay. So if you see this formula here, that we are having thermal conductivity as one of the property here. So let's define what is thermal conductivity. So from this expression, I can write that K is equal to Q dot into delta X divided upon A into delta T. I can write from this expression. I have written from this expression that is K is equal to Q dot into delta X divided by A into delta T. So could you present from other account, the one with the paper? Uh, is there any problem? Are you not able to see it? Any problem is there? Let me know. It's fine now. Fine. So what I was saying, you can write in this form. So if I have to define thermal conductivity, I can define it the rate of heat transfer per unit area normal to the direction of heat transfer per unit temperature difference for unit thickness. I can define the thermal conductivity as the rate of heat transfer per unit area normal to the direction of heat transfer for unit temperature difference for unit thickness. So if I want to write the unit for thermal conductivity, the unit will be watt. Now this is having unit as meter, this is meter square. So watt per meter Kelvin. So the thermal conductivity has unit as watt per meter Kelvin. Now, what is the significance of this property is that the thermal conductivity indicates the material's ability to conduct heat. So it indicates material's ability to conduct heat. Now there is another term you must have come across earlier also in thermodynamics, that is Cp. So Cp is specific heat capacity. So specific heat capacity is a measure of material's ability to store thermal energy. It is material's ability to store thermal energy. Okay. Now, if I write for water and iron, the values for thermal conductivity and Cp. So, for Cp for water is 4.18 kilojoule per kg degree centigrade. For Cp for iron is 0.45 kilojoule per kg degree centigrade. Now, if I write for the thermal conductivity, so thermal conductivity of water is 0.607 watt per meter Kelvin, while for iron the thermal conductivity is 80.2 watt per meter. So you can see here the Cp of water is just 10 times of that of iron. So that indicates the water can store 10 times the energy that iron can. Well, if you see the values of thermal conductivity here, so that indicates the iron is having thermal conductivity more than 100 times. I would say it's not more than 100 times. Yeah, more than 100 times than that of the water. So I can say here that water is a poor heat conductor but excellent medium to store thermal energy. So I can say water is poor conductor but excellent medium to store energy. So that's why water is generally used as working fluid in most of the power plants. Now this thermal conductivity depends upon certain factors. Such factors are material structure. So as I told you, the thermal conductivity depends upon how material is close packed. So the lattice component of thermal conductivity strongly depends on the way the molecules are arranged. So I would give an example to you for that. So diamond, which is having a very close packed structure. So thermal conductivity here, K, depends on first the material structure. So diamond, I was telling about diamond that is having a thermal conductivity of 2300 watt per meter degree centigrade. So it is having very high value of thermal conductivity. So it is having a very close packed structure. Now the second factor on which the thermal conductivity depends is the moisture content. So if you take an example of a porous material, okay, so if there is a damp porous material and a dry porous material, so I can say the damp material is having higher value of thermal conductivity than that of a dry material. The reason behind it is that there is a capillary movement of water into the porous material. So that's why Since the water is having better thermal conductivity than that porous material, so it acts as a medium for conducting heat. So the thermal conductivity of a damp material is greater than that of dry material. Now the third factor is the density of the material. So thermal conductivity increases with the increase in density. So in case of porous solids and powders, the thermal conductivity increases with the density. For example, for asbestos powder, for asbestos, asbestos powder, its thermal conductivity is ranging from zero point 0.1 to 0.25 watt per meter Kelvin, for the density ranging for in the range of 400 to 800 kg per meter. So for porous material, as the density increases, the thermal conductivity increases. Why? Because the thermal conductivity of air filling the pores is much less than that of the solid constituents of the porous material. Now the fourth factor is temperature. The fourth factor is temperature. So thermal conductivity of most metals decreases with the increasing temperature. The thermal conductivity of metals decreases with increase in temperature. How is K damp is greater than K dry? Yeah. So I just told you, for if you consider a porous material, okay. So if there is damp material, there is water present into it. Okay. So water is having better thermal conductivity value than air. Okay. So when water is having better thermal conductivity than air, so in that case, your thermal conductivity in that case would be higher for it. Yeah. So now I was telling that the thermal conductivity, sorry, I missed here conductivity here. Thermal conductivity of metals decreases with increasing temperature. Okay. So the exceptions here are aluminum and uranium. Now this decrement in thermal conductivity can be also mentioned as K is equal to K naught 1 plus beta. So where beta is the coefficient of thermal conductivity, K naught is the reference thermal conductivity at 0 degree centigrade. So beta is negative for metals. It increases with temperature. Why do we assume it is constant for Fourier's law? Okay. Okay, 1 second. I will explain that. Give me a minute. Okay. So beta is negative for metals. Okay. Now for metals, the thermal conductivity is mainly a function of the motion of the free electrons. As I already told you, in case of solid, either it is due to lattice vibration or due to free electrons. So for metals, the thermal conductivity is mainly a function of the motion of the free electrons. So as temperature increases, molecular vibrations increase. In turn, decreases the mean free path of the molecules. So they obstruct the flow of free electrons, thus reducing conductivity, while for the non-metals, there are no free electrons, so conductivity increases with respect to temperature. So for non-metals, your K increases with increasing temperature. So for non-metals, beta is positive. Beta is positive for non-metals. Now, if we talk about the liquids, the thermal conductivity decreases with temperature for most of the liquids. But water is an exception there. Now, if we talk about the gases, the value of thermal conductivity increases with increasing temperature. So, why it happens in case of gases? Because thermal conductivity depends upon the mean free path of the molecules. So in gases, the value of thermal conductivity increases with increasing temperature. Now, there was one question. It is asking, sir, if K increases with temperature, why do we assume it's constant throughout in the Fourier's law? Uh, we are right now considering thermal conductivity to be constant here for the simplification. If you, we will discuss it later on. What is the effect of a variable thermal conductivity with respect to temperature, and what would be the expression for it? We will discuss it later on. For here now, I am just considering the basic law. The basic law of heat conduction, that was the Fourier's law of heat conduction. So it is defined here as Q equal to minus Ka dt by dx. If you want to include the variation of temperature, you can have this K as a function of temperature. So in that case, you can apply integral, and then you can find the value for the heat transfer if the variation of the thermal conductivity with respect to temperature is available to you. So we are going to discuss that later on. Just now, I am just referring here to the basic law. So the basic law of heat conduction is the Fourier's law of heat conduction. Now the other question is, can you repeat the thermal conductivity for liquid? Yeah. So for thermal conductivity of liquid, thermal conductivity for most of the liquid decreases with increase in the temperature. But water is an exception. So in our campus, we are having KD2 Pro instrument. If you sometime come to the campus and you get a chance to do some experiment with it, you can see for a temperature of 15 degrees centigrade, you will find the thermal conductivity as 0.589 watt per meter Kelvin. As you go forward to maybe to 40 degrees centigrade, you will find the thermal conductivity as 0.62 watt per meter Kelvin. So your thermal conductivity, you will observe that the water, for water, it is increasing with respect to temperature. I hope everything is clarified up to this point. Okay. Now the next part which we need to discuss is about the, okay, what is the reason for the water exception? Okay, so for liquids, generally intermolecular forces comes into play. So as the temperature is increased, these intermolecular forces are going to decrease, and the molecules are going to gain energy, and there will be a collision. So in that case, generally for the liquids, when the density will decrease, the molecules intermolecular forces are going to decrease with respect to temperature, and the molecules starts colliding and start exchanging energy with one another. So in that case, your thermal conductivity is going to increase with respect to temperature. For other liquids, your density is very high. So this only the water is an exception, that is, its thermal conductivity is going to increase with respect to temperature. Shall we move forward now? Okay, so our next topic is you are saying that number of free electrons in metals increases with respect to temperature. So I told that for metals, thermal conductivity is mainly a function of the motion of the free electrons. Okay, so as the temperature is going to increase, molecular vibrations are going to increase. So when this molecular vibration has increased, it hinders the path of the free flow of the free electrons, thus reducing its thermal conductivity. I hope now it is clear. Okay. So all of you are mentioning that the image is blurred. I think it is a light problem or a shadow of the mobile because I am recording it with the mobile, so it might be a shadow of it. If there is any problem, you can tell me. I can fix it somehow. This is the best here I can do here setting. I hope you are able to see. Oh, you are asking for the last page again. Okay. Yeah. So this is the last page here. So let's move to the next topic. That is the thermal resistance. So our heat transfer has an analogy with the flow of electricity. So if we consider electric resistance and the current flowing through it, I can write for Ohm's law that is V equal to IR. Okay. So here the potential difference is the potential and the current is the effect. So I can have this written as I is equal to V by R. Okay. Where current is the effect, that is the potential difference is the potential. So if you see the heat transfer definition by the basic Fourier law of heat conduction, that is Q dot is equal to delta T by dx upon delta x upon Ka. Yes, sure, I will upload these notes on the Moodle. Don't worry. Delta x by Ka. Also, the lecture is recorded, so lecture will be also available. You can go to Google Classroom and you can watch it again. Also, the class notes will be also uploaded. So, what I was saying that Q dot is equal to delta T by delta x by Ka, that is by Fourier's law of heat conduction. So, now there is an analogy between these two. You can see here, current is the effect. So, in the heat transfer is the effect. Here, potential difference is the potential. Here, temperature difference is the potential. So, now you can have this resistance. So I can say this value in the denominator is the resistance to the heat transfer, to the flow of heat in a medium. So I can write the resistance or the thermal resistance, H stands for thermal. So thermal resistance for the process of conduction is equal to delta x upon Ka, where delta x is the thickness of medium, K is thermal conductivity, A is the area normal to the direction of heat transfer. So this is termed to as the thermal resistance for the process of conduction. Now let us move to the second mode of heat transfer, that is the convection. So we have already seen what do you mean by convection. So convection is the mode of heat energy transfer or heat transfer between a solid surface and the adjacent liquid or gas that is in motion. So if I am having a hot surface here, okay, and let us consider there is a bulk fluid motion over this hot surface here, okay. So this hot surface, let us consider it is having temperature as Ts, okay, And this bulk fluid which is flowing over this hot surface is having temperature as T infinity, velocity as U infinity. Okay. So the process of convection states that it is the mode of heat transfer between a solid surface and the adjacent liquid or gas that is in motion. Now, if there is no presence of bulk motion, in that case, the heat transfer is only due to conduction. In absence of bulk fluid motion, heat transfer is due to conduction. Okay. So now if there is a bulk fluid motion, in that case your mechanism of heat transfer is going to be convection. Okay. So faster the fluid motion, better would be the convective heat transfer from the surface, or more and more heat will be convected away from the surface. So let us consider that there is hot surface and this bulk fluid motion is over this hot surface with the velocity U infinity and temperature T infinity. Now, as a consequence of fluid surface interaction, there is a development of region in the fluid. There is a development of region in the fluid where the velocity varies from 0, that is at the surface, to finite value, that is U infinity. So here U was 0, here it is U equal to U infinity. Okay. So the fluid that is in direct contact with the solid surface sticks to the surface due to viscous effects, and there is no slip. So because of the viscous effects, one of the fluid layer sticks to the surface and decrease the velocity of the layers which is further away. So it leads to the development of a region within the flow. So the region because of which the fluid stuck to the surface is due to the viscous effects, and the phenomena is termed to be as the no slip, or this condition is said to be as a no slip condition, where one of the fluid layer sticks to the surface and attains 0 velocity relative to the surface. So the layer that sticks to the surface slows down the adjacent layer because of the viscous forces between the fluid layers, which also slows the next fluid layer and so on. So therefore, no slip condition is responsible for the development of the velocity profile. This velocity profile, that is U respect to y. If you consider this to be y direction, this to be x direction. So there is a development of a velocity profile in the flow. So the flow gradients are significant. No, sorry, the velocity gradients are significant in this particular region, and this is termed to be as the hydrodynamic boundary layer. This is termed to be as the hydrodynamic boundary layer, where there is the existence of the velocity gradients. That is, the velocity is varying from U equal to 0 to U equal to U infinity. Yeah, okay. Okay, fine. I will stop at this point. So, next class we will discuss the convection process and the basic law of convection. So, if you have any problem, you can write me a mail or you can write in the chat box. We can discuss in the next class also. I will upload the lecture as well as this class notes on the Moodle. You can watch it again. Okay. Thank you, class.
Excuse me, sir.
Yeah, tell me.
Yeah, so for conduction, you told that the area normal to the direction of the heat transfer is the area that's taken. So the
Yeah.
area normal to the direction of the heat transfer, or the normal area vector, like, do we take the area
So,
vector as normal?
okay. Okay, understood your point. So let us consider this
Yes,
is
sir.
your uh, take something here. Yeah. So this is your any medium here, okay? And
Yes,
this
sir.
side is at temperature T1, this side is at temperature T2 here, okay? So the heat transfer is taking throughout the thickness of the material here, okay? So the area through which it is taking place, that is the area, this area, that is at T1 to T2. So this is the normal to the direction of heat transfer.
Okay, sir. Thank you, sir.
Sir, I have a doubt. What if, sir,